The apple pie, a classic dessert. If someone asked you how to bake an apple pie from scratch, you might typically start by covering the ingredients needed. The eggs, flour, sugar, salt, butter, apples, cinnamon, and so on that make up an apple pie. Followed by all the preparation steps of making the dough, making the filling, and more to turn those raw ingredients into a delicious apple pie. The famous astrophysicist Carl Sagan, however, described the steps to bake an apple pie somewhat differently, saying, "If you wish to make an apple pie from scratch, you must first invent the universe." Dr. Sagan, in this quote, is saying that the world is more complex than we appreciate, that there is more to an apple pie than its ingredients, that it took an incredibly complex series of processes and indeed billions of years to even get to the point where those ingredients exist. The same, though on a vastly smaller scale, might be said of a Java application. For the humble Hello World program, if you were to ask, possibly many, Java developers what code is being executed in the Hello World application, there might be an intuition to suggest it is only the code on screen. The Hello World class, the main method, the system out print line. The reality is far stranger, as to even get to the point of where the JVM executes the system out print line, the JVM must go through a long, complex series of steps including detecting system resources, preparing the environment, and loading and initializing hundreds of classes. One might even say, if you wish to say hello world, you must first invent the universe. And in this episode of Stackwalker, we're going to look into how the JVM builds this metaphorical universe by taking a deep dive into the JVM startup process. If you'd like to learn more about the JVM, finding your nearest Java meetup to talk with fellow Java developers about the JVM, and more, be sure to check out dev.java, link in the description. The exact process the JVM goes through at startup is highly dependent upon the structure of the application, the VM arguments passed in, available system resources, and more. Trying to cover all these possible paths simultaneously would be difficult, so we will just cover the simple Hello World program with logging enabled to demonstrate the key steps. The area of JVM Startup we will be covering is only up until just before user code starts to be executed within the main method, but that should still be enough to cover all the important points of JVM Startup. Throughout this video, I will regularly be referencing the JVM specification, specifically the version for JDK 23, as that is the most recent, link on screen and in the description. Though at the level I will be covering JVM Startup, there shouldn't be much difference with JDK 21 and only a few small differences from JDK 8, I believe most regarding how class data is stored. I will also be using the Hotspot JVM implementation as my concrete example. This is by far the most widely used JVM implementation, as many other OpenJDK distributions also use Hotspot as well. Though several other JVM implementations do exist, and so their behavior might differ from what I cover in this video, I will try to note Hotspot-specific implementation details as they come up. Okay, with those disclaimers disclaimed, let's begin stepping through the JVM startup process by starting at the very beginning. When you execute the Java command, passing VM arguments, and reference a main class, this kicks off the JVM startup process. By calling JNI create Java VM, a JNI Java native interface function with a rather descriptive name for creating a new JVM instance. JNI would be a subject large enough for a Stackwalker episode itself, maybe even two. But in short, JNI is an interface layer that allows the JVM two-way communication with native system libraries. The first steps in JNI create Java VM function is to perform parsing and validation of the VM arguments and main class file that are passed in for correctness, as well as some internal checking. Assuming no fatal issues are found, this will start the process of creating a new JVM, while JNI create Java VM continues to perform some important work, including a check of available system resources, which includes checking for the number of available processors, is NMT, native memory tracking, available system memory, and checking of various other OS utilities the JVM might use. These are important steps in driving the JVM's internal heuristics unless otherwise specified for configuring the initial state of the JVM. For example, the availability of processors and memory dictates which garbage collector is selected. In most cases, the G1GC is the default garbage collector. However, if the system only has a single processor available, or less than 1,792 megabytes of system memory, then this serial GC would be selected. Though in my case, my system easily has enough resources to support the G1GC. The next set of steps involves the JVM setting up its environment, which includes creating HSPerf data, which stands for Hotspot Performance Data. Needless to say, a hotspot-specific implementation detail. This data can be used by tools like JConsole and Visual VM to inspect and profile the performance of a JVM. It's stored in the temp directory on Unix systems. Next would be the selecting and configuring of the garbage collector. As mentioned earlier, in this case, based on internal heuristics, the G1 garbage collector was selected. If CDS is being used, a default behavior, the Serid archive is located and loaded. Loading classes from the Serid archive improves the performance of JVM Startup. I'll return to the subject a bit later in this video. Next in JVM Initialization is the creation of metaspace. Metaspace is a special memory region that's not on the heap, but also directly created in native memory. It is where class data is stored, more on that a bit later. While metaspace is not located on heap, it can still be managed by the garbage collector, and its memory can be reclaimed if class data is associated with a class loader that is no longer accessible. Also, a final note. Metaspace is a hotspot-specific implementation detail, though all JVM implementations would have an equivalent area for storing class data, which is called the method area in the JVM specification. So to quickly review, already the JVM has performed several important steps including parsing inputs, detecting system resources, and preparing the environment, which includes creating HSPerf data, initializing the GC, initializing CDS, and initializing metaspace. Got all that? Good. Because the next part, I'm going to be breaking out charts to explain all the JVM is doing. So let's talk about the meaty part of JVM Startup, class loading, linking, and initialization. And for that, let's go back to that chart, filling it in this time. It represents at a high level the relationship and order of work within the class loading, linking, and initialization processes. But notice, for example, resolution could occur from when a class is being verified to after it's initialized. So while we will be covering each of these processes sequentially, they are not necessarily happening in that order. Okay, let's start exploring each of these concepts in depth. By starting with the process that definitely occurs first, class loading. Class loading is covered under section 5.3 of the JVM specification. It is the process of locating the binary representation of a class or interface and the JVM deriving the class or interface from that binary representation and loading it into the method area, which again would be metaspace in the hotspot JVM as we covered in the previous section. One of the great powers of the JVM and why it's become such a widely used platform is its ability to dynamically load classes. This behavior allows for the on-demand code generation and loading of classes, which is extremely useful for frameworks like Spring, testing tools like Mockito, and indeed, it's even used within the JDK itself for the creation of Lambda call sites. The JVM specification allows for two ways of loading classes, either with the Bootstrap class loader as covered under section 5.3.1 of the JVM specification, or a user-defined class loader under section 5.3.2. The latter would be an implementation of the abstract class Java Lang class loader. However, all the class loading we will be covering in this video will be done by the Bootstrap class loader, a special machine code class loader that's instantiated in the latter stages of JNI create Java VM function covered in the previous section. Let's again return to the Hello World class. No, I want to look at the real Hello World class. Perfection. As the Hello World class, like all classes in Java, has object as its superclass, either directly or indirectly, as object is a root class for all Java classes. However, to initialize hello world, object must first be initialized, which let's take a look at it. Object has methods that should be familiar to all Java developers. getClass, hashcode, equals to string, and so on. Typically, instance methods would only be resolved when they are actually called, but as object is a special class, all methods are resolved, which is interesting for toString and getClass as they involve class references themselves, string and class respectively. If we inspect string, it implements several interfaces: serializable, comparable, char sequence, constable, and constant desc. If we were to look at the logs that JVM is producing on startup, we would see that these classes, or in this case interfaces, are loaded in their declaration order before string is then loaded. Going over to class, we see this pattern repeated, with all the implemented interfaces being loaded, except for serializable and constable, which have already been loaded before class is loaded. This process continues as the bootstrap loader loads classes as it traverses the tree of classes it needs to execute the Hello World class. When classes are loaded initially, they are in what is called a larval state, where the classes API is almost entirely hidden from other classes. This is to allow an opportunity for several important steps to happen, including verification of the class and the class to do its internal housekeeping. So let's take a look at the steps that a class must go through to mature into its adult form. After being loaded, a class is eligible to be linked. Linking, covered under section 5.4 of the JVM specification, actually covers several distinct and important processes, including verification, preparation, and resolution. However, if we return to the chart from earlier, the processes of verification, preparation, and resolution don't necessarily occur in that order. Resolution can be done either eagerly or lazily, so it could happen as early as during verification to as late as after class initialization. But because they are defined in the JVM specification in the order of verification, preparation, and resolution, that's the order I will cover them. Verification 5.4.1 is a process of ensuring the class or interface is structurally correct. This process might also kick off the loading of other classes if needed, though classes loaded as a result aren't required to be verified or prepared themselves. However, in most normal settings, JDK classes won't go through the verification step. This is because JDK classes will typically be loaded from the classes.jsa archive, an archive distributed with the JDK, which, among other things, contain classes that have already been verified. Loading from this archive saves time on JVM Startup and is a part of CDS. Indeed, this slide is from my Stackwalker episode on CDS, which you can check by clicking on the link in the top right or in the description. I would also recommend not committing the acronym CDS to memory, as it's being replaced by AOT ahead of time, a subject we will return to when we look at the future of JVM Startup. Back to verification, one class that does need to be verified would be our main class, Hello World. If we scan through the logs, we will see, somewhat confusingly prepended by the logging tags class and init, the Hello World class is being verified by the JVM for structural correctness. Preparation handles the initialization of static fields to their default values. To better understand this, let's use this simple example class, which contains three fields: myStaticInt, myStaticInitializedInt, and myInstanceInt. In this example, both myStaticInt and myStaticInitializedInt would be initialized to 0, the default for a primitive int type. MyInstanceInt isn't initialized as it's an instance field, not a class field. Finally, there is a resolution process. The resolution process is about resolving symbolic references to a class's constant pool when a JVM instruction is executed. To better understand this, let's return to the earlier myClass example. If we were to use the Java P tool on myClass, we would get an idea of what the JVM actually sees if it were to load this class, which the full output looks like this, which, don't worry, we'll go through all of it. Focusing on the output of Java P, this is a representation of the default constructor generated from myClass. Currently within a constructor, the first code always executed is a call to a parent class's constructor. This is what the JVM instruction invoke special refers to, a call to the default constructor of Java Lang object, the parent class of myClass. To the right of invoke special is the number 1. This is a reference to the class's constant pool. Which, if we were to take a look at that, number 1 is the method definition reference to the constructor of Java Lang object. This is what init refers to. We will circle back to that in a moment. We can also see that this constant pool entry also references constant pool entries 2 and 3, which they themselves reference 4, 5, and 6. In total, even the very simple myClass example has 23 entries in the constant pool. So as you can imagine, classes of actual business importance can have very large constant pools. To connect all this together, these entries would only be resolved if and when the JVM attempts to execute a JVM instruction in a class, which could happen as early as during verification to as late as after a class is initialized. Doing this lazily is all about saving time and memory, as it's possible that not every class that is loaded will be initialized. For example, the Security Manager class, which is on its way out, is loaded but never initialized during the execution of the Hello World application. Regardless, let's now get into class initialization. Class initialization is the last of the JVM processes we will be covering. So the first and very important note, class initialization is not the same thing as instance initialization, i.e. when you call a constructor on a class. Class initialization, covered under section 5.5, involves the process of assigning non-final static fields and executing static initializer blocks. Class initialization is started when the JVM invokes any of new getStatic, putStatic, or invokeStatic instructions on a class. A class's initialization is governed by the special noargs method void clinit, which is separate and distinct from initializing an instance of a class, which is handled by init, which is also automatically created for each constructor within a class, as we saw with Java Lang object from earlier. Returning to clinit, it's a special method because this signature must match exactly for the JVM to call it, and 2, angle brackets are not valid, so it's not possible to write this method with normal Java code. Instead, this method is automatically generated when running the Java bytecode compiler javac. This is also the case for the init method as well. It's not a guarantee that this method is always created, it's only needed if there are static blocks or fields within a class. If a class has neither, then clinit is not generated, and the JVM immediately marks the class as initialized. Which, returning for the last time to this chart, is why class resolution might sometimes happen after a class is initialized. A class that does have a clinit method, however, is the myClass example from earlier, which contained 2 static fields and a static initializer. We can see what the clinit method is doing if we inspect the earlier Java P output, though it's confusingly called simply static. But we can see that during its execution, the myStaticInt and myStaticInitializeInt fields are set with the putStatic JVM instructions, while myInstanceInt is, as expected, not part of the class's initialization process. But these processes of class loading, linking, and initialization continues for the eternity, in at least computer terms, of 62 milliseconds, before finally entering the user code of our main method and printing out Hello World. The JVM has at last created its metaphorical universe for saying Hello World. So we have explored the current state of JVM Startup. What does the future hold? Well, in truth, this is a very exciting time for JVM Startup, with it undergoing some of its most substantial changes in years. Most of these changes are being done as a part of Project Leiden, an OpenJDK project that is looking to improve the startup, time to peak performance, and reduce the footprint of the JVM. The first of the Leiden JEPs that will be incorporated into a major JDK release, in fact JDK 24 coming out in March of 2025, will be JEP 4a3, ahead of time class loading and linking, which of course we just covered in this video. Related, I mentioned CDS earlier, which makes up an important foundation for Project Leiden. However, with all the changes being added with Project Leiden is also a name change. The acronym CDS, which originally stood for Class Data Sharing and now stands for Cache Data Storage, is being replaced with AOT to better encompass the new features being added as a part of Project Leiden. Indeed, many of the features in Project Lightning primarily feature ahead of time AOT in their name. If you'd like to learn more about Project Lightning, be sure to check out my Inside Java newsletter episode on it, as well as this presentation by Dan Heidinga and EOA Lam at JVMLS. So let's review some of the key elements of this video. What did we learn? Well, the JVM does a lot of work during startup. In the space of 62 milliseconds, along with very heavy logging being done, the JVM was able to load, link, and initialize some 450 classes. Not bad. How can this help you? Frankly, in most cases, not a whole lot. There might be some cases it's helpful for debugging purposes. Perhaps the most actionable might be if you're particularly startup performance obsessed, while still needing the JVM's dynamic class loading ability. In which case, with some clever usage of static fields, initializers, and triggering class loading, along with taking advantage of new JVM features like JEP 483, might allow you to further juice your startup performance. Though, a note of caution. The first-party code you write and maintain is often just a small fraction of the code being executed by the JVM, as much of the code being executed will be the dependent code, the frameworks, libraries, indeed the JDK itself you depend upon. So spending a bunch of time refactoring classes to push more of its behavior into the class loading and linking phases might not yield measurable results in startup performance, though may the odds ever be in your favor should you attempt. Well, that's it for this episode of Stackwalker. Until next time, have a good one.